Hello everyone, welcome to our presentation. Today we're going to explore an exciting topic, the structure of the atom. This is the first slide, and it sets the stage for what's to come. We'll be looking at the basics of atomic structure, understanding its components, and seeing how it all fits together. I'm glad you're here, so let's get started. Let's take a quick look at the contents of today's presentation. We'll start with the fundamental question: what is an atom? Then, we'll explore the contributions of Dalton's atomic theory, which was a major step in understanding atomic structure. Moving on, we'll examine protons, neutrons, and electrons. These are the core particles that make up atoms. We'll also delve into different models of the atom, including J.J. Thomson's model and Rutherford's model, along with Rutherford's key observations that led to our current understanding. Bohr's model will come into the picture, highlighting how electrons are arranged in orbits. Additionally, we'll discuss isotopes and isobars, which are variations of atoms with different neutron or mass numbers. Electronic configuration and valency are crucial for understanding how atoms interact and bond with each other. By the end, I hope you'll see how all these concepts connect to form the foundation of atomic science and help us understand the behavior of matter around us. Let's explore the fundamental building blocks of matter by understanding what an atom is. At its core, an atom is the smallest unit of an element that retains its properties. Now, within each atom, there are even smaller particles called subatomic particles. These are the tiny components that make up the atom and are crucial to understanding how atoms behave and interact. The main subatomic particles we focus on are protons, neutrons, and electrons. Protons carry a positive charge and are found in the nucleus, which is the atom's central core. Neutrons are neutral, meaning they have no charge, and they also reside in the nucleus. Electrons are negatively charged and orbit the nucleus in regions called electron clouds or shells. Recognizing these particles helps us understand the atom's structure, its stability, and how it forms the basis for all matter around us. By grasping these concepts, we can better appreciate how atoms build up everything we see and touch in the universe. Let's talk about protons. In 1886, a scientist named E. Goldstein made an important discovery. He found evidence for a positively charged particle, which we now call the proton. He used a device called a cathode ray tube with holes in it to observe these particles. What he noticed was quite interesting. These rays traveled in the opposite direction from the cathode rays. He named these rays canal rays. Goldstein showed that these rays were made up of particles carrying a positive charge. Now, in terms of mass, protons are significantly heavier than electrons, about 2,000 times heavier, in fact. When we write about protons, we often denote them as P+. Their mass is standardized as 1 atomic mass unit, and they carry a charge of +1. Understanding protons is crucial because they form the core of atomic structure, helping us explain the overall behavior of atoms and how they interact. This discovery was a key step in advancing our knowledge of atomic particles and the building blocks of matter. Let's talk about neutrons. In 1932, J. Chadwick made a groundbreaking discovery of a new subatomic particle. This particle had no electric charge, which means it was neutral, and it had a mass of about 1 atomic mass unit, or AMU, which is roughly equal to the mass of a proton. Because of this, it was named the neutron. Neutrons are found in the nucleus of almost every atom. They play a crucial role in stabilizing the nucleus, especially in larger atoms. The only exception is hydrogen, which usually has just a single proton and no neutrons. When we represent a neutron, we simply use the symbol N. And a quick reminder: the atomic mass of an atom is essentially the total number of protons plus neutrons in its nucleus. This sum gives us the overall mass of the atom. Understanding neutrons helps us grasp how atoms are built and why they behave the way they do, which ties into the larger picture of atomic structure we've been exploring. Let's talk about electrons. These tiny particles are fundamental to understanding how atoms and molecules behave. Electrons are negatively charged, which means they play a crucial role in electrical conductivity and chemical reactions. Their movement around the nucleus creates electric currents, which are essential in everything from powering our devices to biological processes in our bodies. What's really fascinating is that electrons don't just orbit randomly. They exist in specific energy levels or shells. When they jump between these levels, they emit or absorb energy, which explains phenomena like light emission. Connecting this to the bigger picture, electrons are at the core of modern physics and chemistry. They help us understand the structure of matter and the interactions that govern the universe. So, grasping the behavior of electrons is key to unlocking many scientific and technological advancements. Let's talk about Dalton's atomic theory. Dalton proposed that the atom was indivisible and indestructible, which was a groundbreaking idea at the time. However, as science advanced, we discovered subatomic particles like electrons and protons, which showed that atoms are not indivisible after all. This discovery challenged Dalton's original concept and made us realize we needed to understand how these particles are arranged within an atom. To explain this, many scientists proposed different atomic models. The first notable one was by J.J. Thomson, who suggested the plum pudding model, where electrons were embedded within a positive sphere. Then, Ernest Rutherford conducted some crucial experiments, like the gold foil experiment, which led him to propose a new model with a small, dense nucleus at the center of the atom. Following Rutherford, Niels Bohr introduced a model that improved upon Rutherford. By explaining how electrons orbit the nucleus in specific energy levels, which addressed some of the issues raised earlier. Connecting this all to the bigger picture, these models show how our understanding of the atom evolved over time, moving from Dalton's simple idea to more complex and accurate representations, helping us better grasp the fundamental building blocks of matter. So here we see J.J. Thomson's model of the atom, which he compared to a Christmas pudding. Imagine a sphere of positive charge. This is the pudding, and embedded within it are the electrons, which he likened to currants or dry fruits in the pudding. To help visualize this, think of a watermelon. The red part is the positive charge, and the tiny seeds inside are the electrons. Thomson proposed that the atom is basically a positively charged sphere with electrons scattered throughout it. This means that the negative charges, these electrons, are embedded inside a positive matrix, creating a sort of uniform mixture. An important point here is that the positive and negative charges are equal in magnitude, so the overall atom remains electrically neutral. This balance is crucial because it explains why atoms are stable and don't just fly apart. So, in essence, Thomson's model gave us a foundational idea of the atom as a positively charged pudding, with negatively charged electrons embedded within. This was a significant step in understanding atomic structure and set the stage for future discoveries. Let's talk about Rutherford's model. Ernest Rutherford was curious about how electrons are arranged inside an atom. So, he designed an experiment where he directed fast-moving alpha particles, which are essentially doubly charged helium ions, at a very thin sheet of gold foil. He chose gold because he wanted the layer to be as thin as possible, about 1,000 atoms thick, to get a clear view of what was happening inside. Now, these alpha particles have quite a bit of energy because they have a mass of 4 atomic units and carry a double positive charge. Rutherford expected that, when these particles hit the gold atoms, they would mostly pass through or be slightly deflected by the electrons and the nucleus. Since alpha particles are much heavier than protons, he didn't anticipate seeing large deflections. This experiment was crucial because it challenged the existing ideas of the atom's structure and led to the discovery of the nucleus, a tiny, dense, positively charged core. It's a key step in understanding atomic structure and the overall theme of how we've come to our current models of the atom. Now, let's take a closer look at Rutherford's observations. What he discovered was truly groundbreaking for our understanding of atomic structure. By conducting his famous gold foil experiment, Rutherford observed that most alpha particles passed straight through the foil, which suggested that atoms are mostly empty space. However, some particles were deflected at large angles, and a few even bounced straight back. This was a key moment because it indicated that there must be a dense, positively charged core at the center of the atom. Rutherford called this the nucleus. These observations challenged the earlier plum pudding model and set the stage for our modern understanding of the atom. So, in essence, Rutherford's work revealed the atom's true structure: empty space with a tiny, dense nucleus at the center. And this discovery is foundational to how we think about matter today. Now, let's discuss some of the drawbacks of Rutherford's model of the atom. Based on his experiment, Rutherford proposed the nuclear model, which highlighted that an atom has a positively charged center called the nucleus, where nearly all of the atom's mass is concentrated. That's a key point to remember. Most of the atom's mass is in the nucleus. However, there are some issues with this model. One major problem is related to the stability of electrons orbiting the nucleus. Rutherford suggested that electrons revolve around the nucleus in circular paths, but this raises a question. According to classical physics, any charged particle moving in a circle undergoes acceleration and should radiate energy. If electrons kept losing energy, they would spiral into the nucleus, making the atom highly unstable. But in reality, atoms are quite stable, so this was a significant inconsistency. Another important aspect is that the size of the nucleus is extremely small compared to the size of the entire atom. This helps explain why atoms are mostly empty space, with a tiny, dense core at the center. So, while Rutherford's model gave us a breakthrough understanding of atomic structure, these drawbacks pointed to the need for further refinement and new theories to fully explain atomic stability. Now, to address some of the issues with Rutherford's model, Niels Bohr proposed a new way of looking at the atom. He introduced the idea that electrons can only occupy certain specific orbits around the nucleus. These are what he called discrete orbits, or energy levels. The key point here is that electrons are restricted to these particular paths, rather than moving randomly. Another important concept is that while electrons are circling in these fixed orbits, they do not emit energy. This was a crucial departure from earlier ideas, because classical physics suggested that any charged particle in motion should radiate energy and eventually spiral into the nucleus. Bohr's model explained why atoms are stable in this way. These energy levels are often labeled with letters like K, L, M, N, or with numbers, such as N equals 1, 2, 3, 4. These labels help us understand and identify the different shells or orbits where electrons can reside. This model was a significant step forward because it introduced quantization into atomic structure, connecting the behavior of electrons to specific energy states. And as we'll see later, this idea helps explain phenomena like spectral lines and atomic emissions. Let's talk about valency, which is basically the combining capacity of atoms. It tells us how eager an atom is to react and form molecules, whether with atoms of the same element or different elements. Now, valency depends on the outermost shell of electrons. The key idea here is that the outer shell wants to have a full set of 8 electrons, known as an octet. Atoms achieve this octet by sharing, gaining, or losing electrons. The number of electrons they gain, lose, or share to reach that octet directly determines their valency. For example, if an element is a nonmetal with 5, 6, or 7 electrons in its outer shell, you find its valency by subtracting the number of electrons in that outer shell from 8. On the other hand, if the element is a metal with 1, 2, or 3 electrons in its outer shell, then its valency is simply equal to the number of electrons in that outer shell. And just to connect this to the overall theme, understanding valency helps us predict how atoms will bond and form compounds, which is fundamental in chemistry. Now, in the context of the first 18 elements, their atoms have specific electron distributions across different shells, which influence their valency and bonding behavior. Let's talk about isotopes, which are fascinating because they are essentially the same element but with a twist. They have the same number of protons, which we call the atomic number, or Z, but they differ in the number of neutrons. This means their mass number, A, varies from one isotope to another. For example, take hydrogen. It has 3 common isotopes: protium, which has just 1 proton and no neutrons, deuterium, with 1 proton and 1 neutron, and tritium, which has 1 proton and 2 neutrons. Now, even though isotopes are chemically very similar, since they share the same electrons, they can have unique properties that make them very useful. Most of the time, we don't need to worry about which isotope we're using because their chemical behavior is identical. But some isotopes are special because of their physical or nuclear properties. For example, an isotope of uranium is used as fuel in nuclear reactors, harnessing its ability to undergo fission. Cobalt isotopes are employed in cancer treatment, acting as radiation sources to target tumors. And iodine isotopes are used to treat goiter, helping to regulate thyroid function. So, understanding isotopes isn't just about atomic structure. It's also about how these variants find important applications across energy, medicine, and health. This connects back to the broader theme of how atomic science impacts real-world technologies and treatments. Let's take a closer look at two elements: calcium, which has an atomic number of 20, and argon, with an atomic number of 18. Now, what's interesting here is that although these two atoms have different numbers of electrons, since calcium has 20 and argon has 18, their mass numbers are actually the same, both being 40. This means that the total number of nucleons, which are protons and neutrons, is identical in both atoms. This brings us to a key concept called isobars. Isobars are atoms of different elements that have the same mass number but different atomic numbers. It's a fascinating aspect because it shows how atoms can have the same overall mass yet differ in their electronic structure and elemental identity. Understanding isobars helps us grasp the nuances of atomic structure and how elements relate to each other in terms of mass, even when their proton counts differ. It connects directly to our overall theme of atomic properties and how they influence the behavior and classification of elements.